Yeah, I think it's fine. Okay.
Reflections are not bad.
Yeah, it'll just be like a small picture in the corner anyway. So, okay, all right. Hello, everyone. I'm Professor Sarah Dean, an assistant professor in the computer science department at Cornell University.
And I'm Andrew Taylor, a PhD student at Caltech, advised by Professor Aaron Ames.
And today we will both talk about our work on developing certifiably safe nonlinear control when there are sensor and dynamics uncertainties. So this work is motivated by the existence of complex systems and complex sensors. In particular, robotic systems are used in uncertain environments and also make use of very complex sensors. And these complexities mean that we can't rely entirely on models of the system, but require some sort of calibration in order to get them to work. So this one picture is probably familiar to many people if you've ever used OpenCV. This is how you calibrate a camera. And this calibration procedure is, of course, using a bunch of data collected by the camera, right, with this special checkerboard. But calibration problems also arise not just in maybe sensing modalities, but also even the physical dynamics of a system. For example, this RC car that you might have constructed using some open sourced tooling, and you didn't quite get the measurements right. And so the dynamics model will be slightly miscalibrated compared to the idealized version. And the fact that these calibration problems need to be solved means that there might be errors in the resulting measurement and dynamics models. So let's think about the setting of feedback control first. This is a way that we can build robots that are going to definitely guarantee the properties that we need them to. And so in this setting, we have, our little robot in closed loop with a controller, where that controller was designed using some model of the system's dynamics, as well as how the measurements from the system correspond to the system state. And we need to design these controllers for properties like stability, so the robot doesn't fall over, safety, so we don't crash into a wall, but also, of course, performance, so that we operate efficiently and achieve the tasks that we want. Now, as I just kind of motivated, there's a bunch of calibration that goes into this process. These models don't just come from physics, but they actually come from a calibration procedure, which is often driven by data. And so this is kind of the picture I want to have in my head about data-driven feedback control. Of course, as we use our controller on the system, we might collect additional data and add that to our repository, potentially using it for calibration later on. This kind of secondary feedback loop is especially common in applications like reinforcement learning. Today, though, I actually want to focus primarily on the guarantees that we can make arising from the data that we use for calibration. So I'm actually not going to focus so much on this arrow of collecting more data in closed loop, but I am going to think about how the data that we have to learn from affects the guarantees we can make about our models, and then also resultingly about the controller. So the goal is to build controllers for robotic systems that guarantee safety and stability despite uncertainty in the measurement and dynamics models. So now I'll go into a little bit of background on a method of nonlinear control that allows us to guarantee things like stability and safety, even when we do know these models perfectly. And then I'll talk about two problems arising from uncertainties, first in measurement and then later in dynamics. And then we'll end with a discussion of some dirty laundry and some open problems. Now, this is based on joint work with Andrew, of course, who will jump in halfway through, but also many other collaborators, Aaron Ames, Ryan Cosner, Victor Duran-Bantu, Ben Recht, and Yisang Yu, many of whom are at Caltech and one of whom is at Berkeley. Now, the setting that we're going to consider throughout this talk is a nonlinear control setting, where the dynamics are given by these nonlinear control affine dynamics, meaning that the functions f of x and g of x might not be linear in the state, but the derivative x dot, the dynamics of the system, are affine in the control input u. And we'll have the state is n-dimensional and the input is m-dimensional. the goal of nonlinear control is to design a controller K, a feedback controller K of X, which certifies some desired behavior, so that when we use this controller in closed loop with our system, for example, a robot, we guarantee that the robot won't fall over. The approach that I'm going to take and that I'll introduce is based on control certificate functions. These control certificate functions allow us to encode a control objective, like stability and safety, on the basis of instantaneous system behavior. So rather than reasoning about long-term trajectories, which is quite difficult in nonlinear systems, we can reason really about the instantaneous behavior while guaranteeing these longer-term objectives. Now, a control certificate function approach has two pieces. The major one is a certificate function, which maps states to real numbers. And the secondary component is a comparison function, alpha, which maps real numbers to real numbers. The core of this approach is the control certificate condition, which says that the time derivative of the certificate function should be bounded by the comparison function of the certificate function at a given state. And this time derivative depends on x dot, which in turn depends on both x and u. So this is a condition on inputs and states. What we focus on is the set of inputs which satisfy this condition at a given state. And we think of our controllers as living in this set, such that at each state, the controller gives us an input which then causes this condition to be satisfied. And when that's true, we can guarantee desired behavior. So far, this is an abstract, set of equations, and it's an abstract framework for putting together a control objective into the language of this instantaneous condition. So to maybe make this more concrete, I'll go through two examples of control certificate functions that some of you may have seen before. Our first example is control-Lyapunov functions. Here, the certificate function, which we might call specifically the Lyapunov function, needs to satisfy this condition, which essentially says that it should be increasing away from the origin and always positive. And the comparison function should essentially be increasing. And when the Lyapunov function and the comparison function fit into those classes, then our control certificate condition means that the origin is stable. So our system is stable to the origin. And to use this constructively, we can actually use the control certificate condition as a constraint in an optimization-based controller. What this QP does is project any kind of hand-designed controller, KD, onto the set of inputs which satisfy that control certificate condition. And that means that this K of X will be in that set that we said was good, and therefore the system will remain stable. Now, another example is rather than guaranteeing stability, we might be more interested in guaranteeing safety. The example in this case is control barrier functions, where we're given a barrier function such that the zero sublevel set, so the states for which the function is less than zero, corresponds to a safe set that we want to ensure our system stays in. So for example, the safe set might be the roadway just inside the white lines. And in this case, we have a comparison function, which is the class kappa extended, which means that it's sort of increasing and off to infinity. In this case, the control certificate function condition, if we can guarantee that condition, then we can say that our safe set is forward invariant, or in other words, as long as we start in that safe set, we remain there forever, thus guaranteeing safety. Similar to the case of control-Lyapunov functions, we can define an optimization-based controller that takes any hand-designed controller and projects it onto this set of safe inputs thus guaranteeing closed loop safety. Now, this is sort of the goal. This is what we would like to do with these functions. But let's zoom in a little bit on this control certificate condition. When are we actually effectively able to do this? So again, let's consider the set of inputs that guarantee the condition at a given state X. Notationally, in some of the future slides, I'm going to replace this inner product between the gradient of the certificate function with the dynamics as the Lie derivatives, L sub f c. And similarly, L sub g c. Now, we call C a control certificate function if this set is non-empty for all X. Why is this important? Well, if we want to use our optimization-based controllers, we want to project onto the set, it better have some elements that are valid. Otherwise, everything is hopeless and our design would be infeasible. And actually designing control certificate functions, in other words, functions that will always satisfy this condition for some U at every state, is a non-trivial task. And there's a lot of work on doing this in data-driven ways or using sum of squares techniques, but it's not going to be the focus of our talk today. Just to motivate why we can gloss over this difficulty, for certain classes of systems, for example, feedback linearizable systems, which many robotic systems are, knowing the degree of actuation is sufficient for designing the control certificate function, even if the system dynamics themselves are unknown. So for the rest of the talk, we'll suppose that some function C, which is a control certificate function, meaning that the set is always non-empty at every X, we'll assume that's known and given to us. And now we'll talk about the fun stuff. How do we use this nonlinear control technique when we don't actually know every part of the system precisely? Because remember, to actually implement some of these controllers, like the CBF QP, we need to be able to enforce this constraint, which requires that we know the state of the system as well as the dynamics. So what do we do when that's not the case and we only have calibrated models? The first setting that I'll talk about is perception. In this case, we assume the dynamics are known. So these control affine dynamics defined by F and G are known, but the state is not perfectly observed. And in fact, we have to reconstruct it from some measurement Y. And in particular, I'm motivated here by perception settings where Y is maybe a high dimensional nonlinear encoding of the state. So suppose I have a robot, I use an image to take a picture of it, and then I use some learned perception component or map to predict the state of the robot. In general, our predicted state X hat as a function of Y will not be exactly the true state, but it will be the true state plus some error term. And the error that I have in prediction will generally depend on the measurement that I took. So how do we deal with this measurement model error? How do we define it or try to grapple with it? The classic statistical story in machine learning is to focus on empirical risk and population risk, where the population risk is the expected loss over some distribution. In other words, how accurate am I at predicting, from an image, the state of the robot over some distribution of images? And there's really a crude understanding of distribution shift, where we might have had one distribution of images for training and then another one at test or operation time. Statistically, these are things we can grapple with, but the bounds that we get in response are quite crude. And in fact, it's unclear that distributional properties are actually strong enough to guarantee stable control. While my training distribution may have relatively small errors, a single point with a high error that I encounter in closed loop could throw everything off track. Instead, if we really want to guarantee something like safety and stability, it's important to focus on uniform convergence to get actual point-wise error bounds. Now, this is something that statistics can give us, but only when we have dense data. The image to have in mind in kind of a non-parametric regression setting, similar to deep learning, although of course a simplification, is one where each data point contributes kind of a little bump to our prediction, right? So around each data point, I think that because the underlying function is smooth, I can roughly predict what will happen. And so my prediction essentially averages up the little bumps that I have from the data that I've observed. In settings like this, we can show that as long as our training data is approximately larger than 1/epsilon to the nth power, then with high probability, this perception error will be bounded by epsilon at every single observation we make y. So this is a uniform error guarantee, not just an average error guarantee, but it requires a very heavy sampling burden with an exponential dependence on the dimension of the state space. So let's suppose that I do have these pointwise error guarantees and I have been able to learn from very dense data. How would I enforce the CCF condition with imperfect state observation? At a high level, our approach is to consider based on the x hat we've estimated, the set of all possible x's that might have generated the measurement that we took. And so rather than enforce the condition precisely at x, which we don't observe, we can consider all x in the uncertainty set and try to guarantee a robust version of the constraint. This leads us to the definition of measurement robust CCFs, which is our main contribution of this work, where we define the set of inputs which ensure robust safety. Notice that this set depends on the measurement that we took rather than the state, and it uses our estimated state. There's also an additional term that depends on some functions A and B, which depend on our measurement and map to positive numbers. Because this term will be positive, it makes the inequality harder to satisfy, which adds robustness to this set of inputs. And the main result is that as long as our perception errors are bounded by some function epsilon of y, and the Lie derivatives and the comparison and certificate functions are Lipschitz, then if we set A and B appropriately, depending on the Lipschitz constants and the error bounds, then any controller contained in this measurement-dependent set certifies the desired behavior of the system. This means that we now have a purely data-driven or a largely data-driven constraint on our optimization-based controller, and because we've robustified it appropriately, it still guarantees the same behavior that we would like. Now, when is this problem feasible? Because of the added robustness, the fact that C is a valid control certificate function no longer guarantees the feasibility by itself. And that means that we may run into infeasibility issues, but we can show that as long as our errors are small enough in a way that depends on each state directly, then we can guarantee feasibility. Essentially, as long as we take dense enough data, right? So we sample the safe set appropriately, we can guarantee feasibility.
Measurement robust control barrier functions have been realized experimentally on a Segway platform as seen in these videos. In the top video, measurement error in the Segway's camera system leads to a collision with obstacles in the Segway's environment, despite the Segway thinking it is still safe as given by the dashed red line in the plot on the upper right. In the bottom video, an MR-CBF-based controller forces the Segway to stop before colliding with the boxes, even in the presence of measurement error. We note that not only does this experimental realization demonstrate the capability of MR-CBFs, but it also shows the feasibility of running more complex convex optimization problem controllers in real time. In further work, we have also realized MR-CBFs on a quadrupedal robot using SLAM to localize itself within an environment populated with obstacles. We observe that the robot is able to successfully avoid collisions with obstacles while progressively navigating its way to a goal location. In the next portion of this talk, we will look at how data can be directly incorporated into convex optimization problems to define control certificate function-based controllers that are robust to model uncertainty. We once again consider a system described by control-fi nonlinear dynamics. Importantly, the functions f and g may not be perfectly known. We will present this construction assuming that these dynamics are entirely unknown, but we note that it is straightforward to incorporate a model of these dynamics into this construction. We'll make the following assumptions. F and g are Lipschitz, and we know upper bounds on the Lipschitz constants of these functions. Second, we will assume that we have access to a data set of states, inputs, and state time derivatives, xi dot. Our goal will be to characterize the functions f and g using the data set in a way that is useful for control synthesis. To this end, given a data point xi, ui, and x dot I, we will build an uncertainty set at each state x, denoted ui of x, that captures possible values of the functions f and g that agree with the data point. We can show by construction that the true values of f and g at the state x must lie in this set. To see this, observe that we may use the dynamics associated with the data point to write the following equality. Rearranging this expression and taking norms, we arrive at this inequality, and using the Lipschitz properties, we can upper bound the left-hand side by the following term. We will denote the right-hand side of this expression, which is purely a function of x, as epsilon I of x, noting its appearance in the definition of the uncertainty set. Considering an uncertainty set constructed for each data point in the data set, we can construct the set u of x as the intersection of all such uncertainty sets, noting that the true values of f and g must lie in this set as they lie in each of the individual ui of x sets. Importantly, proximity to data points reduces possible values of f and g as described by the function epsilon I, as it decays as we move closer to a given data. Given this construction, we seek to construct a controller that allows us to be robust to these possible uncertainties. This can be given by a robust optimization problem specified here. We note that this controller requires that the inequality given by the CCF be met for all possible values of the terms a and b that are in the uncertainty set. We note that this is an infinite set of constraints. The main contribution of this work is to show that we can actually express this optimization problem with an infinite set of constraints as a finite dimensional second-order cone program given on the right. Importantly, the second-order cone program returns a controller that we know will meet the CCF inequality by construction, giving us either stability or safety guarantees as desired. We consider this controller on a simulated inverted pendulum with input gain attenuation. We look at both stability and safety of this system expressed through CCFs. The nominal controller of the system is given by a feedback linearizing controller using an estimate of the system model that neglects uncertain parameters and input gain attenuation. We consider controllers built with two different data sets, both composed of grids in the state space, but with different inputs taken at each point in the state grid, noting that the second set is a proper subset of the first one. We see that in both the stabilization and safety settings, the nominal controller does not achieve the required control objectives. In contrast, the data-driven controllers using both data sets achieve the prescribed goal. In the stabilization case seen on the left, the certificate function c, serving as a Lyapunov function, decays to 0. In the safety case seen on the right, the certificate function c, serving as a barrier function, remains below 0. An important observation is that the data-driven controllers achieve nearly identical behavior, despite one possessing 1/3 of the data. This indicates the ability of this control design to extract relevant information for control decisions, even from limited data. We also study this system in an episodic learning safety setting, where data is aggregated across episodes. We see that as the episodes progress from blue to red, the system monotonically approaches closer and closer to the boundary of the safe set without violating safety. By incorporating additional data across each episode, the controller is required to be robust to less uncertainty and allows less conservative behavior, hence approaching the safe set boundary more closely. In conclusion, we can see that robust CCFs can be used to guarantee safety under uncertainty. The resulting control designs may be also expressed through convex optimization problems. And lastly, the properties of these controllers are inherently linked to the underlying data used to construct the controller itself. So let's talk a little bit about dirty laundry that went into these results. The first is that in the perception setting, the guarantees that we have on safety rely on dense and labeled data, and this data might not be easily accessible or may be difficult to collect with a general robotic system. So this is something that may have to be a challenge when trying to design for very complex systems in the real world. Another issue that we have sort of obscured here is that the robotic demos using MR-CBFs use extensions of the MR-CBF framework. These extensions, while using MR-CBFs, permit more sort of controlled and understandable behavior of the robots. So it's not the direct vanilla MR-CBF implementation, but something that's slightly modified that you can find in the resulting papers. In the unknown dynamics setting, one thing that we have to know is a valid control certificate function. For systems with structure, we may be able to prove that this assumption is justified, but for systems that sort of violate structural assumptions, it may be difficult to know a valid control certificate function a priori, given just a model of the system. Moreover, the SOCP that we produce from our infinite dimensional robust optimization problem scales with the dimensionality of the data set. The more data we add, the more complex this optimization problem becomes and the longer it takes to run. And this suggests the need to find principled techniques for reducing the data set and some sort of pre-processing technique that allows us to work with smaller data sets in our online controllers.
Cool. And then finally, I think some of that dirty laundry brings us back to open questions. So in this talk, we really focus on how data enters into the control design problem. But looking forward, we would really like to incorporate data collection in closed loop and think about how the data that we see during operation can actually help us to improve. Now, in the perception setting, one of the big challenges to this is the fact that in closed loop, we only have unlabeled data, because if we had the state label, then of course we could just use that directly and our problem would have been solved. So dealing with this kind of unsupervised setting is a huge challenge. And also a big opportunity. On the other hand, in the case of unknown dynamics models, we are actually get supervision for free by watching how the state itself evolves. But the problem there is that in closed loop, we collect so much data that it overwhelms the optimization solvers when directly added to the SOCP. And so for that, the open question is, how do we efficiently and in a principled manner down select the data that we've collected? The second open question, the big one, is how do we design control certificate functions which are feasible when they also must be robust and not just feasible when the system is perfectly known? And with that, thank you so much for your attention. These papers are the ones that we drew from in the presentation today, as well as our many references.